Okay. This topic, we need to talk about the system analysis in time domain. That's our topic. And so the objective of this section are, first of all, interpreting free step, ramp, and impulse response. What's the meaning of the free response? Can anyone say that? Anyone remember? It's entirely dependent on what the initial condition, right? Initial condition. It's the free response. Forced response means that forced is entirely depending on the what? The input, right? And also in this topic we need to talk about the system parameter estimation, but based on the what? Based on the tau, wn, right? The natural frequency, time constant, and the zeta. Okay, these are the basis of the R lesson right now. So first of all, we need to deal with the what? Response of first order system. So assume that for the MCK system, mass spring damper system, we can write, or we can have to what? To this kind of equation, mv dot plus cv is equals to the ft, right? We don't have the spring factor in here because we need to write it in the first order system, because if we have the velocity value, and so if we take the derivative of this term, and so we can reach to what? The acceleration, right? If we use the position, and so we will have the second order system, okay? For MC system. So in free response, just remember the free response. It's entirely depending on the what? The initial condition, which means that ft is equals to the what?
0.
Yes, 0. So if we take the Laplace transformation of this term, and then we will have to what? The m times s times vs minus v0. This is the initial condition, plus c times vs equals to the 0, right? These are the Laplace transformation solution for this system. And so the vs can be collected with the what? The m times s plus c, right? Plus c, which is equals to what? The v0 times m. It's coming from the what? The first equation, right? And so after that we will reach to the what? The vs is equals to the what? The v0 times m divided by ms plus c, right? This is our the Laplace transformation form of this equation. Or we can write this equation, vs is equals to the what? v0, and so we divide by m at the both sides, the numerator and denominator in here, and so we will have the s plus c divided by m, right? This is our equation. And so how we can write the solution or the vt in here in time response? How we can write it?
Predicate predefined. This form is predefined.
No, what is the time response of this system?
Minus C over M.
Hmm?
Minus C over M.
Minus C over M. No.
To the power minus
Huh?
C over
What is the solution of this term? We have the constant value in here, V0 times,
E.
yes, exponential over minus
C over M.
T C over M, right? This is the time response. This is the frequency response, right? And so, what's the general formulation of these terms? We can write the Vt is equals to V0 times exponential minus t divided by tau, because in the frequency domain we have the roots in here, but this roots is the inverse value of the time constant in here. And so what is the time constant of this system?
M divided by C.
Hmm?
M divided by C.
M?
Divided by C.
Yes, this is the time constant. Okay. And so if this is the case, see that we can write the three conditions in here. If İlayda, C divided by M is smaller than 0, and then we can say that
It's unstable
yes. Why?
because it goes to infinity.
Yes, because it's minus, and so this minus, and it goes to what? The plus, and so it's always to what? To increase to exponential term. And so what is the condition of the C divided by M is equals to the 0? In this case, İlayda, just put that 0, and so this term
Constant.
constant. Yes, naturally stable. Naturally means that we have the constant value. But what if the C divided by M is greater than 0? It is stable because it goes to the what? To the 0. T infinity V T goes to 0. Okay? Huh.
Vt goes to V0.
No, 0. At the stable case. At the initial position, we have the V0. The initial value of this term is V0. But if we take the C divided by M is greater than 0, and so it always goes to the 0 at this case. Just see the formula. You can see it. Okay? So, what is the dynamic of these terms? Just see that. Just remember the previous lessons. We can draw this kind of outputs in here. This is the Vt and this is the T. And so what is the initial condition? Initial condition is V0, right? Initial condition is that. And so we have this kind of curvatures in here. And just remember the what? The time constant definition. How we can define the time constant in this case? For example, if we have the tau value in here, tau value just like this one at this position is equals to what? The 0.737 V0, right? And so we reach to what? 0.37 point in here, and so this is called to the what? Time constant. Time constant values. And so what about the 4 tau? In the 4 tau, these values closest to the what? The 0.02 times V0. Okay? This is 0.37 V0. This is the time constant, 1 time constant. This is the 4 time constant is equals to what? 0 times 0.2 V0. Okay? Remember that? Okay. So, now we can continue with this information. We need to put the head titles in here. 7.1.2 is the step response of first order system. It's the R topics. And so what about this? For the system of the what M V dot plus CV is equals to the FT, and so at this case FT must be equals to the what? UT, right? This is the unit step. If the T is bigger than 0, and so it always be 1. It's the unit step. Abdurrahman or Abdurrahim. Abdurrahman. Okay. And so what about this? If this is the case, Fs is equals to what? The 1 divided by S, right? Do you remember that? 1 divided by S. Okay. So if we take the Laplace transformation of these terms, and so the M S Vs minus V0, right, plus C Vs is equals to what? The 1 divided by S, right? Right? Okay. And also we can write the Fs values in here, just like this one, because the Fs is constant value. For example, 5, 4, or 1. These are considered as to what? The unit step signal, but with the different coefficients. And so if this is the case, and then we can write it to the what? To this formulation, just like this one. Vs is multiplied to the MSC, which is equals to what? The Fs divided by S, but we have the V0 in here, just like this one, plus V0 M, right? This is the reorganization of the whole equation based on this information. And so what about this one? The Vs is equals to the what right now? The V0 times 1 divided by, or not 1, Ms plus C plus Fs times 1 divided by S times, right? This is 1 divided by Ms plus C. Okay? This is the reorganization of the whole equations in here. And so if we simplify this equation, and then we can write it the V0 times 1 divided by S plus C divided by M plus Fs times, in this case, if we divide the whole the terms into the what? 1 divided by C, and we will have 1 divided by S minus 1 divided by S plus C M. This is the what? This is the expansion form of the each part in here, because if you know the each part just like this one, we can turn into the what? The time domain easy, because we know it to the what? To the inverse Laplace transformation, right? And so if this is the solution, what is the values of the what? The Vt. Just remember that. What is the solution of this term? V0 times yes, minus T times C divided by M plus Ft. This is the constant. Just remember that. 1C and no, 1 divided by S means that 1 minus exponential term minus T C divided by M, right? Because it's the first case, right? This is the R solution. But what is the forced response?
Right side.
Huh?
Right side of the.
Yes, this is the forced response. What is this?
Free.
No.
Free response.
Huh? Free response. Yes. And so if this is the case, we can rewrite this equation based on these terms, just like this one. Vt is equals to what? V0 minus Ft times 1C times E over minus T C divided by M plus Ft times 1C. What is this. And what is this?
Transient and
What is the transient response in here? Yes, left. This is the transient, right? This is steady state, right? We have 4 kind of response in here, just like this one. Okay? We can use it in the what in this domain in terms of the what system parameters. And so, if we know everything about the tau, time constant, and the what, the other coefficients, and also we know the input value, and so we can estimate the parameters or obtain the parameters of these terms in terms of what the time response or time domain, and so we can dominate it, right, Elida? Okay. So, if this is the case, and so we need to continue with the what? 6, the impulse response. What's the meaning of the impulse? Huh? Impulse. It's the instantaneous effect on system. Remember the signal and processing lesson with the what? Unit area, right? Just like this one. The area of this term is equals to the 1, but it goes to the what? The infinity value. But this is goes to what? The 0 minus 0 plus, right? This is a hypothetical input to the system. Right? So, what's the purpose of the impulse? Why do we need to use that?
we can see the effect of the input. We can see the output from this input signal.
Input signal.
So we see UT and see its response on the output.
Yes, but in the correct terms, so
Sisteme sonradan dahil olan herhangi bir kuvvetin kısmı görmek.
no, we can characterize the system by using the impulse response. But how we can do that?
By convolution.
Hmm?
By convolution.
Yes. So, if this is the case, just remember the formula. MV dot plus CV is equal to the FT, right? And so, in the impulse response, if we take the Laplace transformation of these terms as Vs minus V0 plus CVs is equal to what is the Laplace transformation of the what? The impulse response.
1 over x.
No, it's a unit step.
H.
Constant, but it's equal to the 1. If you take the Laplace transform of the unit impulse response, the impulse response, we can convert it as equal to the what? Is equal to the 1. This is curious. In the frequency domain, it has a constant value. Okay, but how we can utilize this property in order to identify the R system in here? If this is the case, and so we can write it just like this one. Vs times Ms plus C is equals to the 1, because we can right now delete this V0 term in here. We don't need to use the initial condition in order to identify the R system. Okay? Because we have the 1 value in here, just like this one. And so, if this is the case, the Vs is equals to the what? 1 divided by M S plus C M. We can remove the initial condition because it doesn't affect the system characterization, because it's outside values V0. we can choose any v0, but the system remains the same, and so we need to delete it. We just apply the impulse response of this term, and so we have the Vs is equal to 1 divided by m plus s plus cm. What is the solution of this term? Vt, yes, exponential term t times c over m. Okay, and so what is that? What's the meaning of this right now? What is the meaning of this? Please be loud.
It's our impulse response.
Impulse response, yes, but what is the meaning of this?
We can use it to predict the output for other.
No.
We can see the effect of the mass on the system.
No. It is the picture. The picture of system in time. This is the general pattern to generate the response based on the what this signal. It is the what, for example, I have a shape, right? I have an x dimension, y dimension, and z dimension, right? And so you can identify me as a Professor İşcan, right? So if this is a system, it's individual parts, okay? And so this individual parts is seen at the time just like this function. Okay? So if you apply an impulse response to me, and so you will get the picture of the what time response of myself. Right? Right? Okay, so if this is the case, and then we have the input, and we have output, okay, and so we have the general pattern or the picture of these terms, just like the impulse, okay, and so this impulse is identified with the ht. So if this is the case, and then we can create the example. Think about the R function and apply ft is equal to the ut, okay, t greater than 0 with u is equal to the 1. This is the unit step, okay. If we know the Laplace transformation, we can easily solve this, but how we can solve in the time domain? Abdurrahman, how we can do that? How we can solve the previous equation based on this u is equal to the 1? How we can solve it in the time domain? But this we know that's how we can solve this equation. Just say that. Convolution. And so the solution Vt is equal to the what? U convolution ht. This is equals to this one, and it's equals to the what? 0 to t u tau times h t tau times d tau. Okay, this is our what? The convolution integral. İlayda. That's it. And so what is the value of this term? It always equals to the 1, right? Okay. So if this is the case, and then this is the first part, in the second part, we can write it to the what? The Vt is equals to the what? 0 to t, and h t times t minus tau d tau is equals to what? The 1 divided by m times 0 t exponential minus c m times t minus tau d tau. Okay, where is it coming from? Where is it coming from? Yes, just see that 1 divided by m e over minus tcm. If we put this ht tau value in here, and so we will reach that form. Okay, and so in the third place we should write that the vt is equals to 1 divided by m e over cm t can be carried to the what, to the left hand side, because it's not dependent on the what, the tau value, right? It's just like the constant value. Do you understand that? Okay, and so 0 to t e cm tau d tau is equals to what, 1 divided by m times e over cm t m c times e cm tau t to 0. And after that we will reach that our last equation is equals to what, the vt is equals to 1 divided by c times 1 minus exponential minus cm t. Okay, this is our to what, our time response for a given ut is equals to the 1. Okay, this is identical with the what, with the Laplace transformation solution. But how is it look like in the graphs? Just see that we have ht, also we have ut. What's the values of the ut? Ya burası çok küçük oldu. Ben dur diğer sayfayı çizeyim. Rahat rahat. ht is the impulse response. This is the ut, and also this is the vt. This ut is equals to the 1, right? This ht is coming from the what, 1 divided by m e over tcm. ht is equals to 1 divided by m times e minus tcm, right? So how we can draw this equation? What's the initial values of the ht? 1 over m, and then it goes to just like this one, right? Right? Okay, and so if we convolve this equation, we should iterate the whole this ut values just like this one. First of all, we need to take the we need to take this part up to tau. Okay, if we convolve this equation, and so what's the general pattern in here? Just move to this line, this rectangle area, to the right direction. Just see that. We move this part just like this one, 0 to t, right? And so at this integral we move this rectangle to the right hand side. And so in the first place we don't have any matching here, just like this one. This area does not match these things, and so the initial values of the vt is equals to what? 0, right? Okay, after that, this is the first part, this is the second part. In this case, if we move to the right hand side, and so this is increased, the matching rate, right? And so this is goes to the what, to this time, right? This is the second, right? But In the second case, this is the unit step signal. This signal is coming from this one, and so it increased the matching rate in here. But in a slowing rate, it goes to the some steady state value. Why? Because the match rate is limited with the exponential term. If it goes to the right hand side, right, and so the matching rate, it always decreases in here, and so the response of this term is equal to what? Just like this one, right? This is the result of impulse response on this term. Okay.